Hello there. I'm glad you've wandered into this little corner of quiet tonight. Wherever you are, allow the edges of your world to soften. Let the stillness gather around you, warm and deep, like the quiet of a planet turning in the dark. Imagine we are sitting by a small, distant light, a tiny beacon in the vast cosmic expanse. Tonight, we're going to lean in and listen to a story of the deep universe, a story that encompasses much more than just the gentle dance of stars. Sometimes, the cosmos is anything but calm. It's a place of astonishing, intense power and unimaginable forces, from the explosive birth of suns to the quiet, crushing gravity of black holes. We'll explore those breathtaking extremes, tracing the incredible mechanisms that both build and break the structures of space. It's a powerful drama unfolding across billions of light years, and yet we are here, right now, gently contemplating it all. There is comfort in understanding this grand scale, in knowing that even the most chaotic event is part of an immense, beautiful order. If this gentle wandering through the deep science helps your mind settle and brings a sense of soft awe, please consider a quiet like and a subscribe. It's a soft way to help other weary minds find their way to this calm, unhurried space. For now, just let the immense, quiet story of the universe begin to settle around you. Close your eyes, and we will drift into the dark together. When people point at a picture of space and say, "This is our solar system," it sounds so simple. 8 main planets circling one ordinary star, more than 150 moons keeping them company, and countless rocks, dust, and drifting gas all sharing the same great turning space. If you could see it from far above, it would look like a thin, glowing disk, 10 billion miles across, like a slow whirlpool of light with the sun at its quiet center. It has been like this for billions of years. Our planets move along their paths the way a well-made clock keeps time. Each world follows its own lane, not crashing, not wandering too far, not straying too close. There is a kind of calm in that, a deep, steady order that you don't have to think about. Everything just keeps going, round and round, as if the whole system is breathing in an almost invisible rhythm. But this calm is not the rule of the universe. It is the exception. If you could drift away from our small circle and look at other star systems, you would see that many of them are anything but gentle. Around distant suns, some giant planets rush in so close to their stars that their day-sides glow with fierce heat, their clouds boiled and torn by shock waves that reach thousands of degrees. Their paths are tight, hurried, pulled inward like marbles caught in a drain. There are planets that swoop so near the surfaces of their stars that they almost skim the stellar fire, dipping in and out like stones skipping across water, except the water is made of burning plasma. Elsewhere, huge stars swing around each other in close, dangerous pairs, each one tugging fiercely at the other's light and shape. In some systems, there are not just 2 stars, but 3 or 4, all circling in tangled patterns. Their gravity weaves a web of orbits so complicated that in time, whole worlds can be thrown out, flung into the dark between the stars, abandoned and frozen. What feels calm here, in our little neighborhood, would look like a rare and fragile arrangement from that wider view. Farther out, on even grander scales, the violence grows. There are stars that feed on their neighbors, slowly pulling gas from a companion until one of them explodes. There are black holes, regions where gravity is so strong that not even light can escape, that swallow stars gas clouds, maybe entire planetary systems, grinding them down into hot, swirling disks of matter. And beyond that, whole galaxies, each with billions of suns, sometimes crash through one another, their spiral arms stretching and twisting as they merge, like two ghostly cities drifting together in slow motion. Out there, this chaos is normal. Tumbling orbits, close brushes, collisions, destruction, and rebirth. That is how the universe often works. Against that backdrop, Earth is a quiet island in a stormy sea. Our planet is small and blue, wrapped in thin air and water, warmed just enough by our star. Life covers it, in oceans and forests, on mountaintops, and deep underground. And all of this depends on something that sounds simple, but is almost miraculous in how it has held steady: the way Earth travels around the Sunday. Earth's path is almost a circle, not perfect, but close enough that our distance from the sun stays nearly the same throughout the year. We do not rush in and out on a long stretched loop. We do not spend half our time too close and half too far. Instead, we glide on a track that keeps us in a gentle band of warmth. That near circular orbit is a kind of cradle. Because of it, the sunlight that reaches us does not swing wildly between too much and too little. The result is a planet where temperatures, though they change with the seasons and from place to place, stay mostly within a range that liquid water can survive. Oceans don't freeze solid from pole to equator, and they don't all boil away into space. Rain can fall, rivers can flow, ice caps can grow and melt slowly, and clouds can form and drift. All of those quiet, everyday things depend on a path in space that doesn't wobble too far in the wrong direction. Our orbit has been stable like this for about 4.5 billion years. That long, slow steadiness gave chemistry on Earth time to become something more. In warm seas and tidal pools, in cracks in the rocks and deep ocean vents, simple molecules had hundreds of millions of years to meet, link up, break apart, and try again. Eventually, they formed the building blocks of DNA, the long, twisting code that life uses to remember itself and to grow. That kind of work takes patience on a cosmic scale. If our world had been thrown into wild swings of heat and cold, if our orbit had stretched or twisted too much, the water would not have stayed, the chemistry would not have had time, and all the stories traced inside every living cell would never have begun. So much of what we know and love, forests, music, cities, friendships, even the quiet of this moment, rests on this simple truth: our solar system, and especially Earth's path, is unusually calm. In a violent universe, we have been riding in a place that is gentle enough for life to appear and flourish. In a way, we have won a kind of orbital lottery. But the universe never lets chaos drift too far away. Even inside our own solar system, where things look so well behaved, there are worlds whose paths and conditions are far too harsh for life as we know it. They move under the same sun as we do, yet their orbits turn them toward extremes that no living creature from Earth could survive. The closest planet to the sun is Mercury, a small, rocky world, the tiniest of all the main planets. Instead of tracing a nearly round circle, Mercury follows a stretched-out oval around the Sunday. At its farthest point, it is about 43 million miles away from the solar fire. At its closest, it dives inward to just 28 million miles. That difference may sound like just a number, but under the glare of a star, it matters enormously. When Mercury swings close, the sunlight beating down on its surface is relentless. With almost no atmosphere to spread the heat around or to act as a shield, the the sun's energy falls almost directly onto bare rock. Temperatures can climb to around 800 degrees Fahrenheit, hotter than the inside of a baker's oven, hot enough to melt lead and soften many metals. There are no clouds to soften the light, no seas to carry heat away, no breeze to feel just a silent, burning landscape under a black sky. Because Mercury's air is so thin, it is almost not there at all. A human being standing on that surface without protection would have almost no chance. There would be nothing to breathe, no pressure to keep the delicate balance inside the body. The fluids within you would begin to boil, not because they are heated like water in a pot, but because the lack of pressure would let them escape their liquid state. It's a quiet but deadly kind of harm, a reminder that air is not just something to breathe, but also something that holds us together. Then, as Mercury continues along its path and turns its other face away from the sun, something equally extreme happens. Without a thick blanket of air to trap warmth, the heat gathered during the day pours back out into space. On the night side, temperatures can plunge to about 300 degrees below 0 Fahrenheit, 3 times colder than the coldest winter ever recorded on Earth. The same ground that was glowing with heat becomes a deep freeze. Mercury holds the record for some of the most dramatic temperature swings of any planet in our solar system. Its path around the sun holds another quiet secret. If you could trace Mercury's orbit over thousands of years, slowly drawing a line where it goes each time, you would see that the oval is not fixed. With each circuit, it shifts a little. Over long stretches of time, this moving oval creates a delicate, flower-like pattern, like the petals of a daisy drawn in invisible ink around the sunday. It is a beautiful image for something that is, in the end, still very hostile to life. At the other edge of our solar system lies a very different world, Pluto. It is small, icy, and distant, about 4 billion miles from the sun on average. Out there, sunlight is faint, a pale wash instead of a strong beam. The further an object is from the sun, the slower it moves, and Pluto is no exception. It takes about 248 Earth years for Pluto to complete a single journey around the sunday. That means one Pluto year is longer than the entire history of many human nations and cultures. A person born when Pluto is in one part of its orbit will be long gone before it returns to the same place. Pluto's path is not a neat circle either. It is stretched and tilted, running on a different plane than the major planets. While most of the planets follow a kind of shared, flat disk, Pluto's orbit cuts across that plane, like a thread passing at an angle through a ring. This unusual path means that sometimes Pluto is a bit closer to the sun, and sometimes it is much farther away, spending long ages in the outer dark. For most of its long year, Pluto is like a frozen stone, a mixture of ice and rock locked in deep cold. The surface is coated with frozen nitrogen, methane, and other simple materials, forming plains and ridges of pale ices. The air, if you can call it that, is incredibly thin, almost a whisper of gas above the surface. Temperatures can fall to around 400 degrees below 0 Fahrenheit, a cold so intense that even nitrogen, which makes up most of the air on Earth, turns solid and falls. But as Pluto slowly moves along its stretched-out orbit and comes a little closer to the sun, something gentle and strange happens. That thin sunlight, weak as it is enough to warm the surface just a bit. Some of the frozen nitrogen and methane begin to evaporate, turning from ice into gas. A fragile atmosphere forms, wrapping Pluto in a delicate shell of vapor. It is never thick like Earth's air, but for Pluto, it is a kind of summer. During this time, winds can stir across the surface, and faint hazes can rise into the sky, creating layers of soft, bluish light around the world. For Pluto, this is a season of motion. Then, as it continues its slow path away from the sun again, the temperature drops once more. The gases in the atmosphere begin to freeze and fall back, not like rain as we know it, but as incredibly fine, cold snow made of nitrogen and methane. These tiny particles settle down, building a smooth, glassy, semi-transparent layer over the ground, a frozen atmosphere lying directly on the surface. You can imagine this cycle repeating over and over, 248 Earth years of travel for one complete loop, long eras of deep freeze, then a slow, tentative thaw, then freezing again. For Pluto, seasons last longer than many human lifetimes. Its changing orbit writes slow stories in ice and gas, tales of a world that breathes in centuries instead of seconds. When we look at Mercury, burning and freezing in turn, and at Pluto, drifting through its long winters and brief, fragile summers, we are reminded of how narrow the band of comfort truly is. These worlds share the same sun that warms your skin on a mild day, yet their paths and distances twist their fates toward extremes. Against these examples, Earth's orbit looks even more precious. Our distance from the sun stays within a range that keeps oceans from boiling or freezing solid. Our tilt and path give us seasons, but not ones that last for centuries in darkness or in blinding heat. Our air is thick enough to protect and hold us, thin enough to let warmth escape when it needs to. All of it depends on a balance that is delicate, even if it feels permanent from our short human view. If our gentle path around the sun were nudged even a little, the story we just told would change completely. The same orbit that has quietly protected us for billions of years is also a thin line between very different fates. Move that line inward, just a bit closer to the sun, and Earth begins to look less like the blue world you know, and more like our nearest neighbor, Venus. Venus orbits closer in, wrapped in bright clouds that shine softly in our sky. From far away, it looks calm and beautiful, like a pearl hanging in darkness. But up close, Venus is a warning. Its air is incredibly thick, a heavy blanket made mostly of carbon dioxide that traps heat with terrible efficiency. Sunlight can get in, but the warmth has a hard time getting back out. On the surface, the temperature is close to 900 degrees Fahrenheit, and the pressure of the air is dozens of times higher than what you feel at sea level here. It is so hot, so heavy, and so toxic that no known form of life from Earth could live there. If Earth's orbit were shifted inward, even by a small fraction of our distance from the sun, we would begin to tip toward a future like Venus. More sunlight would pour into our atmosphere and oceans. At first, it might just feel like a warmer world, hotter summers, shrinking ice at the poles. But as temperatures climbed, water in our oceans would evaporate faster. Water vapor is itself a powerful greenhouse gas. The more of it there is in the air, the more heat is trapped, and the cycle feeds on itself. Over long stretches of time, this runaway heating could cause our oceans to slowly boil away into the sky. Seas would turn into a shroud of steam, and then that steam would be broken apart by sunlight and lost to space. The land would dry and crack, forests would burn and not return, and the world that once felt mild and welcoming would become a dry, suffocating desert planet. The sun would be the same, only our distance would have changed. A small push in the other direction could be just as deadly. only colder. If Earth's orbit moved outward by a similar fraction, away from the sun's warmth, our planet would slide toward a frozen state, sometimes called snowball Earth. Temperatures would drop slowly at first. Winters would grow longer, and summers would no longer melt all the winter snow. Year after year, bright white ice would linger, reflecting more of the sun's light back into space instead of letting it warm the ground. As more light was reflected, the planet would cool even further. Glaciers would creep outward from the poles, sea ice would spread toward the equator, and the oceans could freeze over almost entirely, leaving only a thin layer of liquid water deep below the ice. In that frozen world, most forms of life that we know would not survive. The planet that once rang with wind and trees and human voices would fall nearly silent under a shell of ice. What is haunting is that both of these fates, desert furnace and global ice ball, could be triggered by relatively small changes in our orbit. A slight shift inward, and we start to burn. A slight shift outward, and we begin to freeze. We live in a narrow zone between fire and ice, held there by a delicate balance of distance, atmosphere, and motion. Orbits can be gentle cradles for life, but they can just as easily be the cause of ruin. Underneath all of this is a simple truth. Nothing in space stands still. Planets, moons, stars, and galaxies are always moving, tracing paths around one another in a vast, invisible dance. The reason for this motion is a single, quiet force that acts everywhere, all the time: gravity. Gravity is the attraction that every bit of matter feels for every other bit. A falling apple curves toward the Earth because our planet pulls on it. At the same time, the apple pulls on the Earth as well, just more softly, because it is much smaller. The more mass an object has, the stronger its pull. That is why you can jump off a chair but not float away into space. The Earth's gravity keeps you close. In our solar system, the Sun is the heavyweight. It has about 700 times more mass than all the planets combined. That enormous mass gives it a huge gravitational pull. The Sun tugs on every planet, every moon, every comet and asteroid, forever drawing them inward. If this were the whole story, everything would fall straight into the Sun like raindrops into a drain. But there is another piece: motion. The planets are not sitting still near the Sunday. They are speeding through space, each with its own sideways velocity. You can imagine this by thinking of throwing a ball. If you drop it, gravity pulls it straight down. If you toss it forward, it travels in a curve forward and down at the same time. If you could throw it fast enough, and there were no air to slow it down, the ground would curve away beneath it at the same rate that it falls. It would keep missing the ground, always falling but never landing. That is, in a simple way, what an orbit is. Each planet is always falling toward the Sun because of gravity, but it is also always moving sideways fast enough that it keeps missing. The result is a looping path around the Sun, drawn by the pull of gravity and the speed of the planet. Some of these paths are almost perfect circles, others are stretched out ellipses. All of them are just the shapes that motion takes when gravity is in charge. Even small motions near home fit this idea. If you toss a ball up into the air and catch it again, for that brief flight it is in a tiny orbit around the center of the Earth, gravity is always there, bending every motion. If you imagine, just for a moment, that the Sun's gravity could be turned off, the delicate balance of our solar system would vanish. Planets would no longer curve inwards. They would shoot off in straight lines, racing into the dark, never to return. On the other hand, if the planets somehow lost their sideways speeds and stopped moving forward, Gravity would pull them straight down into the sun, one by one. Orbits exist only because these two tendencies, falling inward and flying outward, are perfectly matched. This same balance of pull and motion shapes some of the most peaceful scenes in the night sky and some of the most terrifying objects we can imagine. Among the strangest are black holes. There may be billions of black holes scattered throughout the universe. We cannot see them directly because their gravity is so strong that light itself cannot escape once it gets too close. But we can detect their presence by the way they affect the things around them. The paths of nearby stars, the glow of hot gas swirling as it falls inward, the ripples they send through space-time when they collide. From far away, a black hole is just another object with gravity. Up close, it becomes something much stranger. The pull is so intense that our normal ideas of space and time begin to break down. Equations that work everywhere else start to give answers that seem impossible. Densities without limit, clocks that appear to stop, directions that are no longer clear. We are not going to send people to visit one. The dangers are too great, the distances too vast. But it is tempting to imagine a small robot making a one-way trip toward a black hole, its instruments watching and measuring as it falls. Before it is torn apart, it might send back a last message from the edge of the most extreme environment in the universe. The edge of a black hole is called the event horizon. It is not a solid surface you can land on or touch. Instead, it is more like an invisible boundary, the point of no return. Outside this boundary, light can still escape back into the wider universe. Inside it, nothing, not even light, can get out. For us, the event horizon marks the dividing line between the region of space we can, in principle, see or visit, and a region forever hidden from us. If you were somehow falling toward a black hole, you might not notice the exact instant you crossed this boundary. There would be no sign, no flash, no wall. But once you were inside, every possible path you could take would lead deeper in. There would be no way to turn around, no path back to the outside universe. In that sense, crossing the event horizon seals your fate. As you get closer to the event horizon, gravity grows stronger from place to place across your own body or across the length of a spacecraft. If your feet are closer to the black hole than your head, the pull on your feet will be stronger. Your head, being slightly farther away, feels a bit less pull. The result is a stretching force, gentle at first, then increasing, as if you were a piece of soft candy being pulled from both ends. This stretching has a whimsical name, spaghettification. It sounds almost funny, but what it describes is anything but gentle. As you approach the black hole, the difference in gravity between your nearer side and your farther side grows so large that you are pulled out into a long, thin shape like a strand of spaghetti. A sturdy robot probe would face the same fate, pulled and stretched until its structure fails. But imagine, just as a thought experiment, that we could build a probe strong and flexible enough to endure this stretching and keep working. As it fell closer to the event horizon, something even stranger would happen, not to its metal frame, but to its sense of time. In the regions of extreme gravity near a black hole, time itself does not flow the way it does here on Earth. Strong gravity slows down the passage of time. Close to a black hole, clocks would tick more slowly compared to clocks far away. Right at the event horizon, from the point of view of a distant observer, time for the falling object seems to almost stop. If you were watching our little probe from a safe distance, you would see it approach the black hole and begin to slow down. As it neared the event horizon, its motions would get slower and slower, as if someone were gently pressing a pause button. Signals from the probe would stretch out, their arrival times drifting farther apart. Eventually, it would appear to freeze, hovering at the edge, never quite crossing the boundary. From your point of view, you would never actually see it fall through. It would just grow dimmer and redder until it faded from view. But from the probe's own point of view, its internal clock would continue to tick. Its instruments would keep measuring. Its cameras would keep taking pictures. As far as the probe is concerned, it would cross the event horizon in a finite amount of time and continue inward. Inside, the pull of gravity would draw it toward the heart of the black hole, a region we call the singularity. The singularity is where our current understanding of physics breaks down. In our equations, it shows up as a point where densities become infinite, where the curvature of space-time becomes infinitely sharp, and where familiar ideas of before and after, here and there, seem to lose their meaning. Scientists do not like infinities very much. They are usually a sign that our theories, as beautiful and useful as they may be, are incomplete. Many believe that a deeper description of nature will eventually replace the singularity with something we can make sense of. For now, though, it remains a kind of "here be dragons" mark on our cosmic maps, a reminder that there are still places where our knowledge dissolves into mystery. When we speak of a singularity, we're really admitting something simple and honest. This is the place where our understanding runs out. The word sounds precise and technical, but underneath it is a kind of shrug. It marks the spot in our equations where they stop giving us sensible answers and start whispering, "I don't know." For now, that's where we have to leave the heart of a black hole as a question waiting in the dark. There is, however, one thing we do understand much more clearly. We know how most black holes begin. They are born from stars that have reached the end of their lives. A very massive star shines for millions of years, holding itself up against its own gravity by burning nuclear fuel in its core. When that fuel is gone, the balance fails. Gravity wins. The star collapses inward, crushing its own matter tighter and tighter until, in some cases, nothing can stop it. A black hole forms, a region where the pull of gravity is so strong that even light cannot escape. Many of these stellar mass black holes are small in size, though not in mass. Some are only about 20 miles, or a few dozen kilometers, across from edge to edge. You could drive that distance in less than an hour on a highway, yet within that tiny volume, there can be more mass than in several of our suns. It's like compressing an entire city, every person, every building, every grain of sand, into something smaller than a town. Then there are the giants. Over the last few decades, scientists have found evidence for a different kind of black hole, far larger and heavier than these stellar remnants. We call them supermassive black holes. Instead of being 20 miles across, they can be as large as our entire solar system, or even larger, so wide that if you replaced the sun with one of them, its event horizon would swallow the orbits of many planets. These monsters sit, as far as we can tell, at the centers of most large galaxies, and one of them appears to lie quietly at the heart of our own. Our home star, the Sun, is one of hundreds of billions of stars in a great, flattened collection we call the Milky Way. From a dark place on a clear night, you can sometimes see it as a milky band stretching across the sky, the combined glow of uncountable distant suns. All of those stars, including ours, are moving. They circle around a common center, orbiting something hidden in the middle. Children sometimes ask a question that feels simple but cuts straight to the heart of things. If the moon goes around the Earth and the Earth goes around the sun, what does the sun go around? It's a gentle way of asking where the center really is. Astronomers ask themselves the same thing. For a long time, they suspected there might be something very strange waiting at the core of the Milky Way. Perhaps a black hole so massive that it anchors the whole galaxy. There was a problem, though. We can't see a black hole directly. It gives off no light of its own. The center of the galaxy is also cloaked in dust and gas that block visible light, like a thick fog in space. So the only way to answer the question was to look for clues, to watch the stars near the center and see how they move. If they were whipping around something invisible, their orbits could reveal what was hiding there. To do that, astronomers turned to infrared telescopes, which see longer wavelengths of light that can pass more easily through dust. When they pointed these instruments at the heart of the Milky Way, they saw a crowded, restless region. Millions of stars packed tightly together, all swirling around an unseen center. It was like looking at the lights of a distant city at night, blurred and shimmering, with something dark at its core. One research team devoted years and then decades to this mystery. High above the clouds, on a Hawaiian mountain called Mauna Kea, a giant telescope known as Keck was built, its mirrors housed in a silver dome that opens like a slow eyelid to the sky. From this calm, cold summit, far from city lights, astronomers like Andrea Ghez spent night after night staring into the central glow of our galaxy, tracking the tiniest motions of the stars near its heart. The region they needed to study was incredibly small on the sky, a minuscule patch of darkness surrounded by sparkling points. Finding what they were looking for was truly like searching for a needle in a haystack, except, as one astronomer put it, they knew exactly which handful of hay to watch. The challenge wasn't knowing where to look. It was seeing clearly enough. The air above us is never perfectly still. As starlight travels through Earth's atmosphere, tiny pockets of warm and cool air bend it in slightly different ways. To our eyes, this shows up as the twinkling of stars. To a telescope, it looks like a constant blur. If you want to measure the motion of a star at the center of the galaxy, you need to cut through that blur. The Keck telescope uses a clever trick called adaptive optics. Before it takes its sharpest images, it shines a powerful laser into the sky, creating an artificial star by exciting atoms high in the atmosphere. Instruments watch how the light from this laser star wiggles and dances as the air shifts. Then motors gently bend and twist the telescope's big mirror, sometimes many times a second, to cancel out those distortions. It's a bit like putting on a pair of glasses that constantly adjust themselves, bringing the universe into focus. With this technology, the images from Keck became clear enough to pick out individual stars right next to the galaxy's center and to pinpoint their positions with incredible accuracy. One scientist compared it to standing in Los Angeles and being able to see a person in New York move their finger slightly. That's the level of precision needed and maintained year after year. As the years passed, the team built up a kind of time-lapse movie. Each dot of light in their images was a star, and slowly, patiently, those dots began to trace curves. Some stars followed wide loops, others whipped around the center so quickly that their full orbits could be seen in a human lifetime. By measuring these paths, astronomers could calculate how much mass must be hidden inside the tiny region they were circling. The answer was astonishing. The stars were moving so fast, on orbits so tight, that only something extremely massive and compact could hold them. The data pointed to an object with the mass of millions of suns, squeezed into a space smaller than our solar system. There is nothing we know of that can do that, nothing that fits those numbers, except a supermassive black hole. It sits there, unseen but deeply felt, like a weight at the center of a spinning wheel, shaping the motion of everything around it. Every point of light in those images has made an epic journey to reach us. Light moves incredibly fast, about 670 million miles in a single hour. In 1 second, a beam of light could go around our planet 7 times. Nothing in the universe travels faster. And yet, space is so vast that even at that speed, it can take a very long time for light to cross the distances between stars and galaxies. When a telescope like Hubble looks deep into the universe, it is also looking far back in time. Some of the faintest galaxies it sees are so distant that their light has been traveling for billions of years. The glow we capture tonight left those galaxies when the universe itself was young, when our sun and Earth did not yet exist. In that sense, the sky is a kind of memory. Each star and galaxy, a snapshot from a different moment in cosmic history. Even among the bright stars we see with the naked eye, many are telling us stories from the past. The light from some of them began its journey toward us thousands of years ago, when our distant ancestors were first learning to plant seeds and harvest crops. Other stars sent us their rays a few hundred years ago, when wooden ships crossed oceans and maps were still being filled in. When you look up at those stars now, you are seeing them as they were then, not as they are at this exact moment. The distance between us stretches time. Even our own sun, which feels so immediate and present, is not quite live. It takes about 8 minutes for light to travel from the sun's surface to Earth. The sunshine that warms your face on a clear afternoon left the sun when you were just a few minutes younger. If the sun were to go completely dark this instant, which it won't, we would keep seeing it shine for 8 more minutes before the change reached us. And even that is only part of the story. The light that reaches Earth has already lived a long, crowded life before it ever escapes into space. Deep inside the sun, in its core, the temperature and pressure are so high that hydrogen atoms are pushed together and fused into helium. This process, nuclear fusion, is what powers the sunday. Each time it happens, a small amount of mass is turned into energy, and some of that energy emerges as a photon, a tiny packet of light. You might imagine that once a photon is born, it shoots straight out to space, but the reality is much more tangled. The sun is not empty inside. It is full of hot, dense gas atoms, packed tightly together, jostling and moving. When a photon is created in the core, it travels only a short distance before it bumps into something. An electron, a nucleus, another particle. When that happens, it is absorbed and then re-emitted, sent off again in a new, random direction. It moves a little, hits something, changes direction, moves again, hits something else, over and over. This process is called a random walk, and it really is random from the photon's point of view. It's as if you tried to leave a crowded room, but every few steps someone turned you, gently but insistently, in another direction. You would wander, doubling back, looping around, moving forward and sideways in no particular pattern. Eventually, after an enormous number of steps, you might reach the door by sheer chance. For photons in the sun, the door is the surface, the point where the gas becomes thin enough for them to stream freely into space. On their way there, photons can be absorbed and re-emitted billions upon billions of times, each interaction changing their path and often their color and energy. The journey is not a straight sprint, but a drunkard's walk through a glowing crowd of particles. And while the last part of the trip from the sun's surface to Earth takes only about 8 minutes, the inner wandering can take a very long time. Estimates vary, but many calculations suggest that the energy produced in the core can take thousands, even hundreds of thousands of years, to work its way from the center all the way to the surface. By the time the light we see and feel leaves the sun, the original story of its birth has long since been scrambled. The photons that actually reach your skin on a bright day are the descendants of an ancient event deep inside the sun, a quiet fusion that happened long before any human eyes were here to notice. So when you feel sunlight on your face, you are touching something with a history, energy that began its life in the dense heart of our star, wandered in darkness for ages, then rushed across nearly 100 million miles of space in a matter of minutes to arrive here, in this moment. The same physical rules that send stars into collapse and carve black holes out of light and time also shape this gentle warmth. In a universe where orbits can tear worlds apart and gravity can freeze clocks, a single beam of sunlight is a soft reminder of how long and how patiently the cosmos has been at work. Deep inside the sun, a photon can spend thousands of years wandering, but once it finally reaches the surface, everything changes. After that long, confusing journey inside the star, the last part of its trip is almost shockingly quick. From the sun's surface to the Earth's sky, it's only about 8 minutes of open space. 8 quiet minutes across the empty dark. And then the light that began as a tiny burst of energy in the core arrives here as warmth on your skin, as daylight on leaves, as a soft glow on the walls of your room. These photons are the source of the light we see and the heat we feel, but they do something else as well, something much more dramatic. On their way out, they heat the outer layers of the sun so much that those layers begin to boil and twist. The gas there isn't calm. It churns and swirls, rising and falling, bubbling like water in a pot left too long on the stove. That rough motion sends shock waves racing through the sun's atmosphere and stirs up a constant, restless storm. From far away, the sun looks like a perfect, steady circle of light. Up close, it is anything but peaceful. The surface and the layers above it are full of turbulence, ripples and waves, and pulses that spread around the star. It is so active that, in a way, we can hear it. Not with our ears directly, of course, because sound as we know it cannot travel through the vacuum of space, but instruments can turn the sun's vibrations into audible sound. An orbiting spacecraft called SOHO has been listening to the sun for years. It measures tiny changes in the star's brightness and motion. Then, scientists transform those patterns into notes we can hear. When you listen to that translation, you are hearing the sun's own slow, deep ringing, the star humming to itself. It is not music in the usual sense, but it is rhythm and vibration, the voice of boiling gas and shaking layers, echoing through space. All that movement does more than make waves. The sun is made of plasma, a kind of gas where many of the atoms have lost electrons and carry electric charge. Wherever you have moving electric charge, you have magnetic fields. On the sun, the constant motion of this charged gas generates complex magnetic patterns. Fields twist, break, and reconnect. As the star spins, its magnetic lines are dragged along, tangled like threads being wound too tightly. They can knot, snap, and burst out through the surface. When these magnetic fields push through the sun's surface, they carry loops of plasma with them, forming great arches that rise high into the solar atmosphere and curve back down again. In images from solar observatories, they look like glowing bridges of fire, arching over darker regions. Some of these loops are enormous. You could take the Earth, place it under one of them, and still have thousands of miles of space between our planet and the edges of the arch. They are beautiful, but they are also dangerous. Inside and around these loops, charged particles, electrons, and ions are accelerated to high speeds. Sometimes, when magnetic fields reconnect or collide, these particles are flung outward in powerful bursts. Streams of them flow away from the sun in all directions, carrying energy and magnetic fields with them. This constant outflow is what we call the solar wind. The solar wind is not like a gentle breeze you might feel on your face. It is a thin but fast-moving river of charged particles that sweeps past planets, moons, and everything else in its path. Most of the time, it is steady. Sometimes, especially after big eruptions on the sun, it becomes stronger, more violent, more packed with energy. When those storms wash over Earth, they can rattle our magnetic field, disturb satellites, disrupt radio signals, and, in extreme cases, even affect power systems on the ground. For astronauts traveling beyond the protection of Earth's atmosphere and magnetic shield, intense bursts of solar wind can be a serious hazard, increasing their exposure to radiation. We are far enough away, and our planet's magnetic field is strong enough that most of the time this hidden weather stays invisible to daily life. Sometimes it even brings beauty with it, painting the sky with auroras, curtains of green and red and purple light near the poles. But the same storms that create those shimmering lights are reminders that our calm world is bathed in a steady stream of restless particles from our star. To understand how all of this works, how magnetic loops erupt and how they fling out the solar wind, scientists have tried to recreate pieces of the sun's behavior here on Earth in a safer, smaller form. We can't stand on the sun's surface. We can't even send a probe close enough to hover right above it for long. The heat and radiation would destroy any normal spacecraft. So instead, researchers build miniature suns in laboratories, carefully controlled experiments that mimic some of the same physics. At places like Caltech, teams have set up large vacuum chambers, metal rooms where almost all the air has been pumped out to simulate the near emptiness of space. Inside, they create plasma by sending strong electric currents through gas. Those currents generate magnetic fields, and with the right arrangement, they can produce loops of plasma that look, in tiny form, like the great arcs we see on the Sunday. The loops in the lab are small enough to fit between a person's outstretched arms. The ones on the sun can stretch many times the width of the Earth. The difference in scale is enormous, but the underlying rules, a moving, charged gas, magnetic fields, tension, and release, are the same. That is what makes the experiment so exciting for the scientists who run it. They are not just playing with glowing arcs. They are watching the same kind of behavior that shapes the skin of a star. When two of these lab-made loops interact, they can twist and reconnect, releasing a burst of energy. Instruments record sudden jumps in temperature and changes in the plasma's motion. Those measurements help researchers understand what happens on the sun when its magnetic fields collide. On the star, similar events can take temperatures in parts of the atmosphere from around 10,000 degrees to 10 million degrees in a very short time. That brief, extreme heating pumps energy into the solar wind, giving particles the kick they need to fly away from the sun at high speed. Each time magnetic fields on the sun reshuffle themselves in this violent way, they can send out flares of radiation and clouds of charged particles known as coronal mass ejections. When those clouds head in our direction, they become space weather that we have to deal with. Much like we watch clouds and storms on Earth to know when rain or wind is coming, We are learning to watch the sun's surface and atmosphere to know when a solar storm might arrive. The size and strength of a star make a huge difference. Our sun is fairly modest compared to many stars in the galaxy. Its solar wind can be dangerous to unprotected technology and astronauts, but Earth has survived under its care for billions of years. There are stars out there, though, that are far larger, hotter, and more unstable. One famous example is a star called Eta Carinae, a massive, temperamental object wrapped in gas and dust, known for past eruptions so powerful they reshaped the surrounding nebula. If Earth were somehow orbiting a star like that at a similar distance to where we orbit the Sun now, our situation would be unimaginably harsh. The energy pouring down on our planet would be many times more intense. The solar wind from such a star would be more like a constant storm, a spray of particles so fierce it could strip away our atmosphere over time. The oceans could be boiled away, their water broken apart and carried off into space. Rock on the surface could melt. The gentle balance that makes Earth habitable would be torn apart. Thinking about these extremes can feel unsettling, but it also carries a quiet comfort. It reminds us that our sun, for all its storms and flares, is relatively steady and kind. It gives off enough energy to keep our world warm, but not so much that it destroys us. Its magnetic tantrums can be serious, but they are not the constant, crushing winds of the most massive stars. By studying how stars work, how photons move, how magnetic fields twist, how plasma behaves, we're not just satisfying curiosity, we're also learning how to live safely in this environment. With better understanding, we can design satellites and power systems that are more resistant to solar storms. We can plan space missions around times when the sun is less active. We can build early warning systems that tell us when a strong burst of solar wind is on its way. In the end, the same physics that fills the universe with violence also fills it with light. The sun's energy pushes and pulls, heats and tears, sends out winds that can be both dangerous and beautiful. And yet, across 93 million miles of space, after thousands of years wandering inside a star and 8 bright minutes of flight, that energy arrives here as a sunrise, a warm afternoon, a soft glow on the horizon after the sun has dipped below it. We live in that narrow, gentle space where the storms of a star become the quiet light of an ordinary day. For all the care we take to understand our star, there is one thing we cannot change. Stars are mortal. They look eternal to us because our lives are so brief. But from the moment a star is born, the clock on its fuel begins to tick down. Sooner or later, it will run out. When that happens, gravity, which has been held in check for millions or billions of years, finally wins. And when gravity wins, the story becomes violent. Our sun is no exception. It feels steady and unchanging, rising and setting with such regular rhythm that it becomes part of the background of life. But deep in its core, every second, it is burning through an unimaginable amount of fuel, about 600 million tons of hydrogen, squeezed and fused into helium. That steady burning is what keeps the sun shining, what pushes back against its own weight and keeps it from collapsing. At that pace, the hydrogen in the core will not last forever. The sun has already been shining for about 4.5 billion years, and it has several billion more to go. Roughly 7 billion years from now, give or take, the core will have used up most of its easy-to-reach hydrogen. As that fuel thins out, the fusion reactions that power the star slow down. The outward push they provide weakens. Gravity, always patient, starts to gain the upper hand. With less fusion in the core, there is less pressure to hold the central regions up. The core begins to contract, pulled inward by gravity, but as it shrinks, it heats up. Compressed gas grows hotter, like air in a bicycle pump when you press the handle quickly. That rising temperature changes the story again. The intense heat ignites new layers around the core, and the energy from this deeper burning pushes on the outer layers of the star. When you heat a gas, it tends to expand. The sun's outer layers respond to the extra energy by swelling. The star's surface moves outward, farther from the core. Today, the sun is about 1 million miles across. In its old age, it will balloon to roughly 100 million miles in diameter, 100 times larger than it is now. It will become what astronomers call a red giant, cooler at its surface, but vastly bigger and more luminous, glowing with a deep, ruddy light. You can imagine a sunrise on a far, distant Earth, 7 billion years in the future. It would not be the small, bright, yellow disk you know now, lifting neatly above the horizon. Instead, the whole sky in that direction would blush with red before the sun even appeared. Then a huge, swollen, crimson globe would slowly heave itself into view, filling a frighteningly large part of the sky. The light would be darker in color but overwhelming in intensity, a relentless flood of heat. By then, Earth would no longer be the soft blue world you recognize. As the sun swells and brightens, the temperatures on our planet would climb into the thousands of degrees. The oceans would first steam, then boil away completely, leaving bare rock beneath a choking atmosphere. Continents would soften and slump, mountains melting like wax under a flame. Any trace of oceans, clouds, forests, cities, anything built of water and delicate chemistry would be gone. The phrase, "the last nice day on Earth," is not really a joke. There would come a final time when the sky still looked somewhat familiar, and after that, everything would change. As the sun grows into a red giant, its outer layers will expand so much that they will likely reach, or even pass, the current orbit of Earth. Our planet may be engulfed, swallowed by hot, dilute gas and vaporized. Even if Earth somehow drifted outward as the sun lost mass, the environment would be utterly hostile long before that. Either way, the story of life on this planet ends long before the star's final breath. Inside the swollen sun, the core will continue its own struggle. With hydrogen gone from the central region, the star must rely on other fuels. The hotter, denser core begins to fuse helium into heavier elements like carbon. This process is less stable. The star becomes more temperamental, with energy surges that travel outward in waves. Each pulse of energy pushes on the outer layers, and little by little, those layers are peeled away. From a distance, this would look like the star shedding its outer skin. The gas that once formed its surface and atmosphere is blown into space, forming delicate shells and rings of glowing material around the fading core. Over time, the sun will disintegrate, piece by piece, leaving behind a hot, dense remnant about the size of Earth, a white dwarf surrounded by a faint, colorful nebula made of its own former self. The sun that once lit your days will become a small, bright ember in space, cooling over billions more years. When you stand under our star now and feel its warmth, it is easy to think of it as simple. We look at the sun and say, light is created there, and it shines, and the world is bright. It feels straightforward and gentle. But behind that apparent simplicity lies a chain of events that is anything but simple. From the first fusion in the core to the moment a ray of sunlight touches the ground, each photon's journey is long and tangled. And the story of light is not limited to stars. Earlier, we followed a photon from its birth in the sun's core, bumping and wandering for ages before finally escaping, then racing across space in 8 silent minutes to reach us. That photon is tiny, much smaller than an atom, with no rest mass, always moving at the speed of light. It is one of countless many, streaming out in all directions. Together, they give the sun its brightness and warmth. But photons can come from any place where matter has energy to spare, not just from the hearts of stars. The short answer to the question, where does light come from, is that matter makes it. Whenever matter is above absolute zero, the coldest possible temperature, it has some internal motion. Atoms vibrate, electrons jostle, particles dance. That motion can produce photons. The hotter something is, the more energy its particles have, and the more light it tends to emit. The character of that light, the colors, the brightness, depends on temperature in a very direct way. You can see this in everyday life. A stove coil starts dark, then glows a dull red when it gets hot, and if it becomes even hotter, it will shine orange, then close to white. A piece of metal heated in a flame first seems to redden at the edges, then grows brighter as it warms further. Coals in a fire can look black at a glance, but if you peer into them, you'll see deep reds and oranges flickering from within. All of these things are sending out photons of different energies as their atoms move faster. Stars are extreme versions of this same principle. They are so hot that they pour out enormous amounts of light across many colors, from deep reds to energetic blues and beyond. Our sun, with a surface temperature of roughly 10,000 degrees Fahrenheit, emits most of its energy in the visible range, which suits us nicely because our eyes evolved under its illumination. But the rule doesn't stop with very hot things. Every piece of matter in the universe, as long as it is warmer than absolute zero, gives off some kind of light. Cooler objects simply emit photons with lower energy, in parts of the spectrum we cannot see. A room temperature coffee mug, a wooden table, the walls of your house, your own body, they are all glowing, quietly, in invisible light. We call much of this invisible glow infrared radiation. It is light, in every physical sense, just with wavelengths longer than what the human eye can detect. You experience it as warmth. When you hold your hand near a gently heated surface and feel heat on your skin, some of what you are feeling is infrared photons streaming from the warm object and being absorbed by receptors in your skin. You, too, are a small source of light. Because you are alive and warm, not at absolute zero, your body emits infrared photons all the time. If you could see only in infrared, a dark room full of people would not look dark at all. It would be filled with soft, ghostly silhouettes, each person outlined by their own gentle glow. Special cameras can do this. Night vision devices and thermal imagers show the world in shades of heat, turning our hidden light into colors we can see. Even someone as cool as you, as the original scientist joked, is shining right now, not in bright reds and blues, but in a subtle, constant infrared haze. The light we can see with our eyes is just a narrow slice of a much wider spectrum. When sunlight passes through raindrops or a prism, it spreads out into a rainbow: red, orange, yellow, green, blue, indigo, violet. Each of those colors corresponds to photons with slightly different energies. Red light carries a bit less energy per photon than blue light. Our eyes are tuned to detect only this band, and even within it, we are more sensitive to some colors than others. Beyond the red, the spectrum keeps going into deeper infrared, then into microwaves and radio waves. Beyond the violet, it stretches into ultraviolet, X-rays, and gamma rays. All of these are forms of light, electromagnetic radiation, just at different energies and wavelengths. Our eyes, marvelous as they are imperfect detectors. They show us only a small window of what is really there. When we look up at the sky, we are seeing only the part of the universe that happens to glow in the colors we evolved to notice. Around and beyond that familiar view is a much richer landscape of light, the whisper of radio waves from distant galaxies, the glow of infrared from warm dust clouds, the sharp bite of X-rays from gas spiraling into black holes. With telescopes and instruments that can sense these other kinds of photons, we have gradually learned to see more of the cosmos than our eyes alone ever could. So as you imagine the sun's distant future, its slow swelling into a red giant, its final shedding of light and layers, it helps to remember how much is hidden even in the present. The star that one day will melt mountains and strip away oceans is, for now, a steady source of gentle warmth, sending out an ocean of photons across many colors. Some we see as daylight, some we feel as heat. Many pass us by without any notice at all. We live bathed in this sea of light, our lives unfolding in a narrow band of colors, while the universe quietly shines in others, just beyond the edge of our perception. We've been talking about light as if it were one simple thing, a single kind of glow that our eyes can catch. But the truth is, what we call visible light is only a very narrow band in a much wider ocean. Our eyes are tuned to a small range of energies, like a radio that only picks up one tiny slice of all the stations that are out there. On one side of that slice lie the gentler, lower energy forms of light. If you step in front of a special camera that senses infrared, the picture shows your body shining softly, even in a dark room. That's your warmth turned into color. Humans, animals, stones, warmed by the afternoon sun, even a cup of tea on a table, all of them are glowing with infrared photons. This kind of light carries less energy per photon than the reds and blues we see with our eyes, so we don't perceive it as light in the usual sense. We feel it as heat. On the other side of the visible band are photons that carry more energy than our eyes can handle. Just beyond violet lie ultraviolet rays, then X-rays, and finally gamma rays. These are still light, still waves and particles of the same family, but each photon packs a stronger punch. Some of these rays can pass through skin and flesh, reaching into the body. In small, controlled doses, we use X-rays to see broken bones. In high doses, the same kind of radiation can damage cells and DNA. The sun, with its vast heat and pressure, makes photons of almost every energy. But deep in its core, where nuclear fusion is actually happening, the photons begin their lives at the high-energy end of the spectrum. Each time hydrogen nuclei fuse into helium, a little bit of mass turns into energy, and that energy often emerges as a gamma-ray photon, one of the most energetic kinds of light in the universe. Compared to the gentle yellow-green photons that our eyes see, a fresh gamma ray from the sun's core carries enormous energy, thousands to 1,000,000 times more, depending on the exact numbers you choose. Comic books joke about gamma rays turning people into superheroes, but the reason the joke works at all is that gamma rays really can transform matter. They are powerful enough to knock electrons off atoms, to break apart molecules, to damage living tissue in a way that can be dangerous or deadly. It's a good thing, then, that the photons born in the sun's heart don't simply fly straight out into space as gamma rays. If the sun were an empty, solid shell instead of a huge ball of dense gas, those newborn photons would shoot outward, cross the star in a couple of seconds, and bathe our planet in a storm of high-energy light, not a recipe for a peaceful, life-friendly world. Instead, something more complicated and much kinder happens. Our photon, freshly created as a gamma ray, starts its life at the speed of light, as all photons do. In empty space, nothing can travel faster. At that speed, if there were nothing between the core and the surface of the sun, it would make the trip in about 2 seconds. But between the core and the surface lies not emptiness, but layer upon layer of incredibly hot, dense gas. As soon as the photon begins its journey outward, it runs into trouble. The central regions of the sun are filled with a thick, crowded soup of particles, mostly hydrogen and helium nuclei, along with free electrons, all jostling and moving in the intense heat. Our photon travels a tiny distance, then, inevitably, it meets one of these particles. When it does, it's absorbed. Its energy is taken up by the particle, which then emits a new photon in a random direction. That new photon is not necessarily identical to the old one. Its energy might be divided among several photons, or shifted into a slightly different form. Step by step, collision by collision, the character of the light inside the sun changes. The photons recycle themselves over and over in a kind of endless game of catch. In this environment, the photon's path is not a straight arrow, but a chaotic scribble. It moves outward a little, then sideways, then back inward, then off in some diagonal direction. Each time it is absorbed and re-emitted, it loses some memory of where it wanted to go. The direction keeps being reset, like a person trying to leave a crowded party, but being gently spun around by every guest they bump into. They might eventually reach the door, but only after a long, confused wander. This region of the sun, wrapped around the core, is called the radiation zone. It is made of gas, but not gas as we normally imagine it. The weight of all the layers above squeezes it so tightly that it becomes denser than many solid materials on Earth. If you could scoop up a piece of this gas, ignoring the fact that it's at millions of degrees, it would be much heavier than the same volume of lead. It's as if our photon found itself in a maze made of walls thicker and harder to cross than anything we know here. The distance from the core to the outer edge of this radiation zone is on the order of hundreds of thousands of miles. Our photon knows, in a sense, that it must travel outward through this entire thickness to reach the cooler layers near the surface. But at every step, the dense, opaque gas is there, blocking its way, bouncing it back, turning it around. The temperature in this zone is extreme millions of degrees Fahrenheit, so the particles are moving fast, ready to scatter any light that passes by. Because of all this, the journey that should have taken seconds stretches out into something like an eternity, at least on human timescales. Instead of shooting straight outward, the photon takes an unimaginable number of tiny steps in random directions. Each step is fast. The photon always moves at the speed of light between collisions, but the overall progress is painfully slow. On average, it can take 100,000 years, or even more, for the energy from a single fusion event in the core to work its way to the sun's surface as light. So when you look at the sun in the sky and feel its warmth, the photons that are touching you now began their story long ago. The energy they carry was released deep in the sun's heart, when no humans were here to see it. The light is old, older than the 8 minutes it took to cross space, and older than any moment you remember. In a way, you are feeling the faint echo of reactions that happened during the ancient past of our star. During that long ascent through the radiation zone, the original gamma rays are repeatedly absorbed and re-emitted. With each interaction, their energy is shuffled and spread among many photons. Over time, this process changes the light from very high-energy gamma rays into lower-energy X-rays, then ultraviolet, then visible and infrared light. By the time photons finally reach the sun's surface and escape into space, they are no longer the dangerous gamma rays that were born in the core. They have been softened, transformed into the gentler forms of light that warm and illuminate planets like ours. Beyond the radiation zone lies another layer where energy moves more like boiling water than like wandering light. There, hot gas rises and cooler gas sinks, carrying heat outward through great rolling cells. Photons ride along with this motion, scattering and being absorbed and re-emitted yet again, until they reach a thin layer we see as the surface. Only from there do they get a clear path into space. If you picture all of this at once, the dense core, the crushing radiation zone, the boiling outer layers, the final leap across space, the sun stops being a simple disk of light and becomes a complicated story. A photon's nightmare inside the star is our blessing. The same density that traps and delays high-energy photons also transforms them into something we can live with, turning lethal gamma rays into warm, familiar sunshine. So the next time you stand in a shaft of light and close your eyes, you might imagine the long, crowded journey that light took to find you. It began as a burst of energy in a nuclear furnace, fought its way through a maze denser than lead, wandered for hundreds of thousands of years, and then crossed 93 million miles of quiet space in 8 minutes. And now, for a brief moment, it belongs to you, warming your skin, brightening your room, and then moving on, forever at the speed of light. Deep inside the sun, in the region where our tired photon has been wandering for so long, the gas is pushed into a very special state. The temperatures and pressures there are so intense that the atoms cannot stay politely assembled the way they do in everyday life. They are torn apart. Electrons are ripped away from their nuclei, and what's left is a mixture of positively charged centers and free-roaming electrons. This charged soup is what scientists call plasma. In school, we usually meet 3 states of matter: solids, liquids, and gases. A rock is solid, holding its shape. Water is liquid, flowing, and taking the shape of its container. Air is gas, invisible and light, filling whatever space it can. Those 3 are familiar because they are the ones we live with all the time. The ground under your feet, the water in oceans and showers, the air in your lungs, they fit neatly into that trio. Plasma is sometimes called the 4th state of matter, but in a way, it's actually the first. Out in the universe, it is by far the most common form. Stars are made of plasma. Many nebulae, those glowing clouds of gas between the stars, are plasma. The matter that flows between galaxies is often plasma as well. Compared to that, Earth is a cool, calm corner where solids, liquids, and gentle gases have a rare chance to settle down and stay together. Here at home, it's usually not hot enough or violent enough to create plasma for long. We get small, brief hints of it. A bolt of lightning, for example, is a sudden, fierce path of electrical discharge through the air. The temperatures inside that bright channel can reach tens of thousands of degrees. hotter than the surface of the Sunday. For a fraction of a second, the air along that path becomes plasma atoms, split, electrons freed, everything charged and glowing. Then, almost as quickly, the energy fades, the electrons find their way back to nuclei, and the air returns to being ordinary gas. In the Sun, the conditions needed for plasma are not fleeting, they are the default. The entire radiation zone, stretching hundreds of thousands of miles from the core, is filled with this charged state. For our photon, this is bad news. Plasma doesn't just glow, it also grabs onto light. Neutral atoms, the sort we're used to have, their electrons bound tightly in place. Light can sometimes pass them by without much fuss, especially if its energy doesn't match the way those electrons like to move. But in a plasma, positive and negative charges are everywhere, roaming freely. Light interacts strongly with electric charge, and in such a busy environment, photons almost never get a clean path. They are constantly being pulled into new interactions, absorbed and re-emitted, scattered this way and that. Our photon, born long ago as a high-energy gamma ray, plunges into this charged ocean and immediately runs into one of those particles. For a tiny fraction of a second, its energy is taken in. Then, a new photon is sent off, maybe in a different direction, and with slightly different energy. That new photon doesn't get far either before it hits another particle. Steps are tiny, collisions are constant. You can picture the whole thing as a strange kind of game on an enormous court, the radiation zone as the space of play. The players are the charged particles of the plasma, nuclei and electrons, jostling and moving. The ball is the photon, always moving at full speed between players, never allowed to leave the court. A pass happens every time a photon is absorbed and then re-emitted. The ball rarely goes straight toward the goal. It's thrown sideways, backward, across, and only occasionally in a direction that brings it closer to the edge. From above, if you could somehow watch this game unfold over vast stretches of time, you'd see that, despite the chaos, there is a slow drift. On average, the ball does move from the hotter center toward cooler regions farther out. Each random step is aimless, but the overall pattern is not. The dense, hot plasma in the core gives way to slightly less dense, slightly cooler plasma as you move outward, and in that gradient, energy prefers to leak from hot toward cold. So the photon's path, though utterly unpredictable in detail, gently favors escape. Each collision has another effect. It changes the photon. When the original gamma ray hits a particle and gets re-emitted, the energy can be shared among several photons or redistributed in subtler ways. Over hundreds of thousands of years, with countless collisions, the photon loses some of its punch. What started out as a ferocious gamma ray gradually becomes lower in energy, shifting down the spectrum. First it resembles X-rays, then ultraviolet light, then eventually settles into the range of visible and infrared photons we're more familiar with. In this sense, the sun's plasma doesn't just delay light, it tames it. The same dense, charged environment that traps our photon also transforms it from something that could tear molecules apart into something that can warm a planet's surface without instantly destroying it. It's a slow, bruising process, but the outcome is gentle sunlight. At last, after perhaps 1,000,000 years of this random walk, our photon reaches the outer edge of the radiation zone. The density has dropped compared to the deep core, but it is still far from empty. Above this layer lies another region where energy moves differently. Instead of being passed along mainly by photons being absorbed and re-emitted, heat is carried by the motion of the gas itself. Hot blobs of plasma rise, cooler blobs sink, and the material churns in great rolling cells. This is the sun's convective zone, the internal roller coaster that our photon is about to join. Here, the ride becomes wild. Imagine a pot of water boiling on a stove. Bubbles of hot water rise to the surface, cool, and sink back down, setting up a constant flow. In the sun, this same idea plays out on a scale so large it's almost impossible to picture. Towers of hot plasma can rise tens of thousands of miles, then fold and sink, their patterns overlapping and interacting. This constant motion helps carry energy toward the surface and contributes to the turbulence and magnetic storms we talked about earlier. If you could somehow stand inside this region, ignoring, for a moment, that you would instantly be vaporized, you would hear the star rumbling. The updrafts and downdrafts, the crashes of rising and falling material, would set up waves that ring through the sun's interior. We pick up some of those vibrations as subtle changes in brightness and motion. Turned into sound, they become the deep, strange tones that instruments like Soho record as the song of the Sunday. Compared to many stars, though, our sun is relatively calm. Its convective motions are strong, but not extreme. Its flares, while powerful, are modest on the grand scale of stellar tantrums. To understand what a truly restless star looks like, we can look out into the night at what seems, at first glance, like an ordinary patch of sky. Among the countless points of light, there is a small star, about 8.7 light-years away, known as UV Ceti. To the eye, it's just one faint star among many. But if you watch it carefully with sensitive instruments, you find that it behaves very differently from our Sunday UV. Ceti is a flare star, prone to sudden outbursts. It can brighten rapidly, several times brighter than its usual glow, in less than a minute, then fade again. Imagine a planet circling such a star. For a while, its surface might be bitterly cold, covered in ice under a dim, reddish light. Then, without much warning, the star flares. In a matter of seconds, its brightness can jump 5-fold or more. The sudden surge of energy would blast the planet's surface, melting frozen ground, vaporizing ice, throwing its fragile environment into chaos. Then, just as suddenly, the star dims, and the planet falls back into freezing darkness. The cycle could repeat, again and again, a harsh rhythm of burning and freezing. UV Ceti can go even further. Sometimes, instead of a small flare, it releases what astronomers call a megaflare, an outburst so powerful that the star's brightness can increase 70 or more times over its normal level in a matter of seconds. It's like a stellar heartbeat that skips not one beat but many, pounding hard enough to shake any nearby worlds to their core. If our sun were to unleash a flare like that, even for only a brief time, our world would be in deep trouble. For a minute or two, the sky would blaze far beyond anything we are built to handle. Temperatures at the surface would spike, atmospheres could be stripped away, electronics fried, ecosystems broken. It's the kind of event that would leave little room for witnesses. Thankfully, the sun is not that kind of star. It has its moods, but they are mild compared to the violent temper of UV Ceti. From our vantage point, Earth is safely distant from that little flare star. Its storms cannot touch us. All we receive are faint photons that left during long-ago outbursts, arriving here as tiny changes in a pinpoint of light. For us, UV Ceti is a story rather than a threat, a reminder of how varied stars can be. and how much our own fate depends on the steady, middle-aged calm of our Sunday. So, hovering between the violent plasma deep inside our star and the wild flares of distant suns, we sit in a rare, gentle place. Above us, photons are still arriving, one after another, each with its own long history of collisions and transformations. Around us, the universe is full of plasma and storms and sudden brightness. And here, for now, the light is soft enough to read by, warm enough to grow by, and quiet enough to fall asleep under. The more carefully astronomers watch the sky, the more they notice that flares are not rare habits of a few odd stars. They are common. All across the galaxy, stars flash and crackle. Bursts of light and energy fire off in every direction. And sometimes, those directions line up with us. The closer a star is to Earth, the more its storms matter, because there is less space for the violence to fade before it reaches us. And one star sits far closer than all the others. From the ground, our sun can look steady and polite, a bright circle that rises, sets, and seems unchanged from day to day. But when you remove the glare and look with special instruments, a different picture appears. The calm disk turns out to be a boiling, twisting surface, and the sun reveals its other side. Under the beauty, it is a kind of monster. Solar observatories, circling above Earth's atmosphere, watch the sun in many kinds of light: visible, ultraviolet, X-ray. In their images, flares leap from the surface like sudden white scars. Gigantic explosions erupt along tangled lines of magnetism, surprising even the people who study them every day. These flares are not little sparks. Each one is an event on an almost unimaginable scale. A single large solar flare can release as much energy as hundreds of millions of hydrogen bombs exploding at once. If you tried to compare that to human life, it would be enough energy to run all of our current power use across the whole planet, not just for a year or even 1,000 years, but for millions of years. That's how much power is unleashed in just one violent twitch of the sun's magnetic field. Seen in visible light, a big flare can be as bright as hundreds of billions of trillions of light bulbs all switched on together. But what you see with your eyes is only a small fraction of what is truly being thrown into space. Along with the light you can see, flares send out radio waves, infrared heat, ultraviolet rays that can burn skin, and X-rays that can pierce deep into matter. All of these come at once, packed into a short, intense burst. These are, by far, the biggest explosions that ever happen in our solar system. And yet, at their heart, the force behind flares is something simple and familiar: magnetism. We meet magnetism first in small ways: a magnet sticking to a refrigerator door, a compass needle turning to point north. It feels gentle and almost playful. But in the sun, magnetism is anything but small. The constant stirring of hot, charged plasma deep inside the star creates an immense magnetic field. You can think of it as invisible lines of force threaded through the sun, wrapped around it, twisted and dragged by its rotation and boiling motions. Where those lines are smooth and ordered, nothing dramatic happens. But the sun's surface is restless, and its magnetic field is often knotted and tangled. Vast loops of magnetic force push up through the surface, carrying plasma with them. They rise into the sun's atmosphere as huge arches, sometimes stretching many times the diameter of Earth, from foot to foot. In some places, the field lines twist so tightly and cross so sharply that they can no longer hold their shape. When that happens, the magnetic field can suddenly rearrange itself, snapping into a simpler configuration. This process, called magnetic reconnection, is like a cosmic short circuit. Energy that was stored in the twisted field is released all at once, heating nearby plasma to tens of millions of degrees. The result is a solar flare, a sudden flash of radiation and a powerful blast of charged particles hurled outward. In the hottest parts of a flare, temperatures can reach around 100 million degrees. At these temperatures, atoms cannot stay whole. Everything is torn into bare nuclei and scattered electrons. Waves of this superheated plasma can be launched outward at tremendous speeds, sometimes carrying clouds of gas that travel 1 billion miles or more into space. Compared to a volcano on Earth, the difference in power is astonishing. A large flare and its associated eruption can be millions to tens of millions of times more energetic than the biggest volcanic blast our planet has ever known. So the same basic force that quietly swings a compass needle around a subtle pull guided by Earth's magnetic field also fuels the largest explosions in the solar system when it acts on the scale of a star. Even with all this drama, by cosmic standards, our sun is modest. It is a middle-sized star, not especially massive, not especially fast-spinning, not especially magnetically intense. As astronomers point their telescopes farther out into the galaxy, they find stars whose magnetic fields are far stronger, whose flares are far bigger and more frequent. In some cases, the storms are so extreme that, if one of those stars were as close to us as the sun is now, the outbursts would tear away our atmosphere and erase life on Earth in an instant. These are the realms of megaflares, titanic explosions that make even the sun's worst tantrums look gentle. Some small, dense stars, called magnetars, for example, can release bursts of energy that briefly outshine entire galaxies. Others, like violent flare stars, can leap in brightness dozens or hundreds of times in seconds. Fortunately, all of them are very far away. Their anger is something we can watch, not something we have to survive. Back closer to home, not all violence in space comes from stars. Planets have their own ways of showing how fragile and changeable their surfaces can be. Even a world with no flares at all can surprise us with its storms. More than 100 years ago, astronomers turned their telescopes toward Mars and watched its surface change as the Martian year went by. They saw a dark wave spreading from one of the poles toward the equator. To some, it looked like a sign of life, perhaps springtime growth, vegetation spreading as warmer weather arrived. They knew that Mars, like Earth, is tilted on its axis by about 23 degrees. That tilt gives Mars seasons: spring, summer, autumn, winter. If there were plants there, they might well respond to changing light and warmth, just as forests and fields do here. It was a hopeful idea. But as we came to know Mars better, sending spacecraft to orbit and land there, a different picture emerged. The dark wave those early observers saw was not a sea of growing plants. It was bare rock being revealed by a storm. As spring comes to the Martian hemisphere, sunlight warms the ground and thin atmosphere. Winds start to move. Mars is a dry, dusty world, its surface covered in fine iron oxide particles, the rust-red powder that gives the planet its color. When winds strengthen, they lift this dust into the air, forming storms that can spread and grow. To understand this, it helps to think about seasons in general. Earth takes 1 year to orbit the Sunday. As it moves, its tilted axis causes different hemispheres to lean toward or away from the sun at different times. In January, the northern half of our planet is tipped slightly away, receiving less direct light, and we call that winter. In June, the northern hemisphere leans toward the sun. The light is more direct and lasts longer each day, and we call that summer. The southern hemisphere has the opposite pattern. Mars works in a similar way. Its tilt is close to ours, so it experiences seasons as well. When a Martian hemisphere leans toward the sun, it has its version of spring and summer. More light, more warmth, more energy to drive weather. On Earth, weather can be dramatic, but we are used to its limits. Dust storms, for example, sometimes roll over dry regions. They can be frightening and destructive. In some deserts, walls of dust, called haboobs, can sweep over cities, turning day to night in minutes. In July 2011, a dust storm about 5,000 feet high, almost a kilometer, rolled into Phoenix, Arizona, swallowing buildings and highways in a brown-gray curtain. For a time, the city disappeared under a churning cloud of dirt. When the winds calmed, the dust settled, coating everything in a fine layer. Then life resumed, and the storm became a memory. But even storms like that are local and temporary. They cover a region, a state, a stretch of road, not a whole world. On Mars, dust storms can grow until they cover the entire planet. All it takes is the right starting push. Sunlight, warming, dust-covered ground, creating pockets of hot air that rise. As they rise, cooler air flows in to take their place, and winds begin. Those winds lift dust. The lifted dust absorbs more sunlight, heating the air around it and strengthening the winds even further. The more dust that gets into the atmosphere, the more sunlight is trapped high above the ground instead of warming the surface directly. The system feeds on itself. There is another important difference between Earth and Mars. Here, when dust is kicked up into the atmosphere, sooner or later, rain will fall. Water droplets form around dust particles, grow, and fall back to the ground, washing the air clean. Much of that dust ends up in oceans or lakes, where it settles and stays. Over time, this rainwashing keeps our atmosphere from filling with dust. Mars does not have oceans. It hardly has any liquid water on its surface at all. Its air is thin and very dry. There are no global rains to scrub out the dust. When particles are carried aloft there, they can stay suspended for a long time, drifting slowly, rising and falling with changing winds. And when they finally settle, they land on more dry ground, ready to be picked up again. The dust on Mars is, in a way, endlessly reusable. Because of that, once a dust storm on Mars really gets going, it can grow and last far longer than storms here. Small local storms can link up into larger ones, covering huge areas. Under certain conditions, these can merge into a truly global storm, hiding almost all the planet's surface beneath a high, hazy veil. From orbit, Mars can look like a blank, pale ball, its familiar features erased. On the ground, a rover's solar panels can be coated in dust, its view of the sky dimmed for weeks or months. This incredibly dry atmosphere is both the fuel and the stage for the storms. Without rain to knock dust down, and without seas to swallow it, storms on Mars fade only when the winds weaken and gravity slowly pulls enough dust back toward the surface to clear the air. Not all Martian storms are planet-sized, though some of the most striking are much smaller, weaving delicate paths across the landscape. Cameras on NASA's rovers, small robots trundling over the Martian soil, have captured images and even videos of dust devils, tall, thin columns of swirling dust, winding their way across plains and craters. They look a little like the mini tornadoes that form over dry fields and roads on hot days on Earth, only set against a salmon-colored sky. Dust devils need two basic ingredients: heat from the sun and a dry, dusty surface. Mars has both in abundance. As the morning sun rises higher, it creates patches of warmer ground. Above those patches, air heats up and becomes lighter. It starts to rise, drawing in cooler air from around it. If there is a small twist in the wind, perhaps from a bump in the terrain or a gentle difference in airflow, the rising column can begin to spin. Once the air starts rotating, it can tighten into a narrow vortex, much like water swirling down a drain. The spinning motion helps hold the structure together. As the column moves over the dusty surface, it sucks up fine particles of iron oxide. These tiny grains of rust-red dust give the devil its shape, a visible, spiraling tower against the pale ground. The dust inside the vortex doesn't just ride along. It also helps keep the system going. Iron oxide particles absorb sunlight very well. As they spin in the column, they take in solar energy and radiate heat into the surrounding air. That extra warmth can strengthen the upward flow, keeping the dust devil alive a little longer. It's a self-feeding loop on a small scale, powered by sunlight and shaped by the thin Martian air. On Earth, we can recreate the look of a dust devil in a controlled way, using simple tools: dry ice for cold, strong fans for motion, fine powders for dust, especially in film studios where special effects are made. The swirling columns that appear in movies are often cousins of the real thing, only safer to stand next to. Watching them form in a tank or on a sound stage gives us a way to understand the patterns we see on Mars and to appreciate how a simple combination of heat and dust can build something so graceful and strange. When you step back and listen to all of this as a single story, it fits with what we have seen from the beginning. The universe is full of extremes. Stars flare, their magnetic fields snapping and releasing more energy in seconds than our species could use in millions of years. Some stars unleash mega-flares that would cook a world like ours if we were unfortunate enough to orbit them closely. Planets tilt and spin, their seasons driving storms that can swallow entire worlds or send slender dust devils dancing across empty plains. And yet, here we are, on a planet whose star is mild enough to allow oceans and forests, whose own weather, while sometimes frightening, stays within bounds that living things can adapt to. Above us, the sun's surface is crackling with plasma and tangled magnetism. Far away, Mars is wrapped in thin air and old dust, its storms rising and falling in long, dry cycles. Between these places, in this gentle orbit, light that has wandered for ages in a star's heart arrives as morning through a window, as a quiet glow behind your eyelids, as a soft reminder that even in a violent universe, there are pockets of calm where life can rest and wonder. On Mars, the story of dust devils doesn't end with a single brief swirl. Once the air begins to spin and lift dust, the dust itself feeds the motion. Those tiny grains of iron oxide are very good at soaking up sunlight. As they rise in the column and whirl around, they absorb the sun's energy and then re-radiate heat into the air inside the vortex. That extra warmth makes the air rise even more strongly, which tightens and speeds up the spin. The faster the vortex spins, the better it becomes at pulling more dust off the ground. The more dust it lifts, the more sunlight it absorbs, and the cycle strengthens. With a whole planet's surface coated in fine, loose dust, the supply never truly runs out. A single dust devil can grow taller and stronger as long as the conditions stay right, drawing new material from the endless red blanket beneath it. Some of these twisters reach astonishing sizes. The tallest can climb 6 miles into the thin Martian sky, like ghostly towers stretching from the surface up into the high atmosphere. As they churn upward, they pump fine particles far above the ground, creating a widespread haze. This thin veil of dust changes how sunlight is absorbed and reflected, subtly shaping the planet's temperature and winds. Enough dust, lifted high enough and for long enough, can help tip Mars into a planet-wide storm, where the entire globe is wrapped in a pale, red-brown fog. Even on Mars, storms that huge are rare. Over the last century or so of careful watching, astronomers have recorded only about 10 truly global dust storms. Those are the events that fooled early observers into thinking they were seeing life spreading with the seasons, a dark wave creeping across the planet as spring arrived. They were right about the season, wrong about the cause. What they were really seeing was a megastorm, a world wrapped in its own reusable dust. And still, for all their drama, even these storms are small compared with the weather further out in the solar system. Beyond Mars, the next planet is a giant. Jupiter, the largest planet we have, is a world of swirling bands and storm systems so enormous that Earth would look like a small marble dropped into their paths. Its atmosphere is a deep, layered ocean of hydrogen and helium, with winds that can circle the planet in furious jets. One of its storms, the Great Red Spot, has raged for centuries, larger than our entire world, spinning in the gas. Farther out still, other worlds show their violence in different ways. On Jupiter's moon Io, tidal forces from the giant planet knead the moon's interior like dough, generating heat that powers hundreds of volcanoes. Some of them fling sulfurous material so high that it forms umbrellas of gas and dust that hang in space. On Triton, a moon of Neptune, eruptions of nitrogen gas and dark particles burst from beneath frozen plains, sending geysers many kilometers into the thin air. Volcanoes, whether on hot worlds like Io or icy ones like Triton, are among the most disruptive forces we know. They bury landscapes under ash and lava, reshape coastlines, and fill skies with gas. But out of destruction can come opportunity. Volcanic heat can melt ice, release trapped chemicals, and create pockets where water can be liquid and chemistry can flourish. In that sense, volcanoes can be both destroyers and midwives for the possibility of life. One of the most intriguing examples of this lies around another gas giant, Saturn. Circling it is a moon that, at first glance, looks modest, wrapped in haze, muted in color, far from the sun's warmth. Yet upon closer study, it has become one of the most fascinating places in the entire solar system. This is Titan. Titan is about 3,000 miles across, larger than the planet Mercury. If it orbited the sun on its own, it might have been called a planet. Instead, it is Saturn's moon, moving through space 1 billion miles from the Sunday. What makes Titan stand out is not just its size, but its air. It is the only moon in our solar system with a thick atmosphere. Instead of a bare, airless surface like our moon, Titan is wrapped in a dense, orange-tinged blanket of gas. In many ways, that atmosphere feels strangely familiar. Like Earth's, it is mostly nitrogen. It has pressure at the surface, similar to what you would feel standing under about 15 feet of water on Earth, heavy, but gentle enough that a human, properly protected from the cold and chemistry, could move through it without being crushed. Within that air, there is weather, winds that stir, storms that roll through, rain that falls, rivers that carve channels, and lakes that quietly fill and evaporate. The difference is temperature. Titan is so far from the sun that its surface is around 300 degrees below 0 Fahrenheit. At those temperatures, water is not a liquid. It is as hard as rock. The role water plays in Earth's weather, forming clouds, falling as rain, filling lakes and seas, is taken up on Titan by other substances. There, methane and ethane, which on Earth are gases we find in natural gas and fuel, can exist as liquids. They pool in lakes and seas, flow through riverbeds, and fall from the sky as rain. It is a world where the familiar water cycle has been reimagined in much colder materials. Above Titan's surface, sunlight interacts with methane gas high in the atmosphere. When ultraviolet photons strike methane molecules, they can break them apart and trigger chains of chemical reactions. Those reactions build more complex hydrocarbons, some of which clump together into tiny particles. Over time, these particles drift down, forming a thick haze of organic material, carbon-based compounds that, on Earth, are deeply connected with life. That haze gives Titan its soft, orange glow and fills its atmosphere with the kinds of molecules that living cells use as ingredients. In that sense, Titan is loaded with raw material, simple organics created by sunlight and methane, slowly settling onto a cold surface where they can accumulate. There is a puzzle here. The same sunlight that builds these organics also destroys methane. Over relatively short timescales, the methane in Titan's atmosphere should be broken down. If there were no source replacing it, the methane should gradually vanish, leaving a very different sky. Yet observations show that Titan's air is still full of methane. Something is replenishing it, pumping new gas into the atmosphere to balance what is lost. That something seems to come from within. When the Cassini spacecraft entered orbit around Saturn and began examining Titan closely, it carried instruments that could peer through the haze using infrared light. In those wavelengths, subtle differences in the composition and temperature of the surface become clearer. Among the lakes and plains, Cassini spotted structures that looked like large depressions, one of them possibly as deep as Earth's Grand Canyon, its floor and walls made of unfamiliar ice and rock. Around some of these features, the infrared cameras saw signs of different materials, patches that reflected and emitted heat in ways that didn't match their surroundings. Some scientists have interpreted these hints as evidence of cryovolcanism, volcano-like activity, where the lava is not molten rock but a slushy mixture of water, ammonia, and other substances that are liquids at Titan's frigid temperatures. If that interpretation is correct, then somewhere beneath Titan's frozen crust, there may be reservoirs of relatively warm liquid. When pressure builds or fractures open, that liquid can rise, erupting onto the surface as flows of icy slurry. Compared with the rest of Titan's landscape, barely above absolute zero, those flows would be scorching, even if they are only a little above the freezing point of water. Hot is a relative word, and on Titan, a puddle of 32-degree water-ammonia mix would be one of the warmest things around. Along with water and ammonia, these eruptions might also carry methane and ethane from Titan's interior to the surface and atmosphere. From there, the methane can evaporate, thickening the air and renewing the supply that sunlight steadily whittles away. The persistent haze around Titan, its global orange fog, may owe a great deal to this slow exhalation, gas and vapor released over eons by cryovolcanoes and vents hidden beneath the clouds. For volcanoes of any kind to exist, even icy ones, there must be heat. On Titan, that heat seems to come from two main sources. One is the natural radioactivity of certain elements in its rocks. As radioactive atoms decay, they release energy, warming the surrounding material. Over long spans of time, this can be enough to keep parts of the interior from freezing solid. The other source is tidal heating. Saturn is a massive planet, and its gravity does not pull equally on every part of Titan. As the moon orbits, it is gently but constantly flexed and squeezed. That flexing rubs its interior materials against each other, generating frictional heat. A smaller moon of Saturn, Enceladus, shows this process very clearly. Its south pole erupts with geysers of water vapor and ice grains, driven by tidal heat. Titan is larger and more complex, but similar processes likely stir its depths. Together, radioactive decay and tidal flexing may create pockets within Titan that are warm enough for water mixed with other substances to melt, forming subsurface oceans or chambers. When fractures open pathways to the surface, that liquid can escape, erupting as cryovolcanic flows. In those brief, local moments, a patch of Titan becomes a place where ice behaves like lava and where cold chemistry lies next to pockets of relative warmth. When we think about the conditions needed for life as we know it, we usually list a few basics: a solid surface to stand on, an atmosphere to protect and transport materials, liquid water to act as a solvent, and a source of energy to drive chemical reactions. Earth has all of these at a comfortable temperature. Titan rearranges them into a stranger pattern, but the pieces are still there. The atmosphere is thick and rich in nitrogen and organic molecules. The surface is solid, made of frozen water and other ices, with dunes and hills and basins. Water, while usually locked up as hard ice, may become liquid underground or briefly at the surface near warm eruptions. Energy comes from radioactive decay, tidal heating, and sunlight filtered through the haze. Volcanism of the icy, cryogenic kind could bring all of these together in small, promising pockets. Imagine a cryovolcano on Titan, erupting into the deep cold. For a while, there is a pool or flow of liquid, a mixture of water, ammonia, and other compounds, surrounded by organic-rich ices and bathed in a dense nitrogen atmosphere laced with methane. In that little region, for as long as the heat lasts, there would be everything needed for interesting chemistry to happen: a liquid medium, complex molecules, temperature gradients, and time. If life ever arose in such a place, it would be truly alien. At Titan's surface temperatures, water on its own is rock, not a drink. Methane and ethane can play the role of rivers and lakes. Any living thing there might breathe hydrogen instead of oxygen, using chemical reactions that are sluggish by Earth's standards, but normal in that deep cold. It might swim, not in water, but in lakes of liquid methane at 300 degrees below zero, or drift near shores made of frozen hydrocarbons. Perhaps there are seas of ethane with slow waves lapping against icy coasts. Perhaps there are shallow basins where different liquids mix, forming tide pools of chemical richness. Perhaps, near a cryovolcanic source, there are hot springs by Titan's measure, places where warmth seeps out over long periods, keeping small regions above the surrounding freeze. In such places, if life can exist at all under those conditions, volcanic and hydrothermal activity might give it the start it needs. All of this is speculation, of course. We do not yet know whether Titan hosts anything we could call alive. but the ingredients and the energy are there in a way that keeps drawing our attention back to that distant orange world. And even as thoughts wander so far outward, it's hard not to notice that we may not need to travel 1 billion miles to look for signs of life shaped by volcanoes and ancient water. Closer to home, circling the same sun and sharing some of the same storms of dust and light, lies a smaller, colder world that has already sent pieces of itself to our planet as meteorites. A red planet with a history of volcanoes, valleys, and long, dry riverbeds waits there, offering its own quiet hints. Mars, with its dust devils and global storms, with its frozen ground and buried ice, might be the next place where we listen for a different kind of story. A story not just of orbits and weather and light, but of whether life has ever found a foothold beyond this gentle, fragile world we call home.